the last section of this unit is on voltaic cells. Okay, so we're going to use this reaction here as an example for the next couple of slides. Right, all redox reactions involve the loss or gain of electrons, right? LEO or GER. But take a look at this reaction here. I want you to answer these two questions. What species is being oxidized and what's being reduced? Okay, so the zinc is being oxidized. It's going from an oxidation number of 0 to +2. It's going up. Okay, so it is losing electrons, right, LEO. And the copper 2 ions going from +2 to 0. So it is gaining electrons, it is getting reduced. Okay, so what we want to do here is write out the half reactions. And so in order to do that, we're going to pick out, right, the one that was oxidation. We said that zinc was the oxidation half reaction. And on the left side of the arrow, this is what the zinc looks like. It's solid zinc, right? On the right side of the arrow, it looks like this. It's a zinc +2 ion. And since it's oxidation, it's losing electrons. Well, how many electrons did it lose to go from 0 to +2? Well, it's going to lose 2 electrons to do that. So we're going to put those over on the product side. Okay, then for the reduction half reaction, let's pick the copper, the +2 ion, copper 2 ion, because that's what it looks like on the left side of the arrow. On the right side of the arrow, it looks like Cu, solid copper. And to go from +2 to 0, it had to gain electrons. Well, how many electrons did it gain to go from +2 to 0? Well, it gained 2 electrons. Okay, so it looks like that. So we would call this the half reaction, right? Where you have just the oxidation occurring here and just the reduction occurring right here. So what is a voltaic cell? Essentially, a voltaic cell is a battery. It's going to produce an electric current. These are sometimes also called galvanic cells. These are sometimes called electrochemical cells. All right, those are all names for batteries. Voltaic cells, galvanic cells, electrochemical cell, battery. So what's going to happen? Well, if we take a look at that reaction that we had previously, and we separated out into the half reactions. So over here we have the zinc metal and the zinc ions, and over here we have the copper metal and the copper ions. And we said that zinc is losing electrons to the copper +2. Well, this zinc plate here, right, draw an arrow and then we'll erase it. Oops, let's change the color so you guys can see that. Okay. There's the zinc plate. That's the the solid zinc metal. It's going to lose electrons. Right, that's what these red arrows are indicating. And they're going to go this way through this wire and over to the copper plate, where the copper ions are going to then plate out onto the copper plate. Back over here, the zinc metal is going to become zinc ions over time. Okay. We also have this piece in the middle here called a salt bridge, which we'll say more about here in a minute or two. Okay, as we talk about this. But this is essentially what a battery is. Now, the batteries in your phone, the batteries in your iPad or laptop or calculator, they're not going to look exactly like this, but the idea is still the same, that you've got a flow of electrons from some source to some sink and some sort of bridge in the middle allowing that to happen. Okay, but over here, this is where all of the oxidation is occurring. This is the oxidation half of the reaction. And over here is where the reduction half of this reaction is occurring. So what is a battery officially? A voltaic cell? It's an apparatus that uses a redox reaction to produce electrical energy or uses electrical energy to cause a chemical reaction. Okay, so the half cell is where that half reaction takes place. We already said that the left side of our example here was the oxidation half cell. Okay, and these plates here have names, right? They're generically called electrodes, but when we know which one's oxidation and which one's reduction, we can name it. This plate here on the left side, since that's where oxidation is occurring, that is called the anode. And over here where reduction is occurring, this is called the cathode. Okay, same one as the cathode ray tube, same idea there. Okay, so the electrons, importantly here, flow from the anode to the cathode. They flow from the anode to the cathode. And if you can never remember which one's which, that oxidation is at the anode and reduction occurs at the cathode, the other helpful hint, kind of like Leo and Gurr and oil rig, is people will say red cat. Reduction occurs at the cathode. If you can remember red cat, reduction occurs at the cathode, then you can also remember the other one. People will say an ox. Anode is where oxidation is occurring. Okay, so there's a couple of helpful devices to help you remember which is which. So you have Leo and Gurr to figure out what's oxidation, what's reduction, and red cat and an ox to determine which thing is the anode and which thing is the cathode. Each electrode has its own potential voltage. The voltages are all measured against what's called the standard hydrogen potential, standard hydrogen electrode, which is 0. Okay, so you can make an electrode out of hydrogen. We're not going to see that, at least in person, but we set that one equal to 0, and then you have plus or minus compared to that, and that's how we're going to generate the voltage of a battery. So here they are. They're called standard reduction potentials. They're all listed as reducing, okay? Whether that's what's normally happening to them or not, all right? But you can see there, this is called the cell potential, or the half-cell potential. They're measured in volts. We'll show you how you calculate it here, but you can figure out the voltage of any battery if you know what things are making it up. Don't worry about memorizing this. If you need it, you will be given these values. You can screenshot it if you'd like, but like I said, you'd be given it on a quiz or test in the future. Okay, so going back to our example from just a little bit ago, we knew that the zinc was actually what got oxidized, and the copper +2 ion is what got reduced. Well, how did we know that? Why isn't it that it's the copper ion that gets oxidized and the zinc that gets reduced, right? And that has to do with the potentials, and again, those are from the previous slide, okay? But let's talk about how we know which one's going to occur. The reaction with the highest potential is going to stay the reduction reaction. Okay, so both of these, I pulled them from the previous slide. You can go back and look. They're both listed as reducing, but redox is one reduction reaction and one oxidation reaction. So what we're saying here is the one that's got the highest potential becomes the reduction one. Well, that's the second one here. So that's going to stay the reduction potential, and the one with the lowest one is going to have, well, it's going to become the oxidation one, right? In which case this arrow would get flipped, right? Because in order for it to oxidize, it's going from 0 to +2, right? It's going backwards. So right, in order for you to figure out which one is correct, okay, the highest potential is going to be the reduction. So since the second one is reduction and the first one will turn around and be oxidation, we're going to rewrite the first one backwards as zinc 2, the zinc +2 ion, and 2 electrons. Now, when we combine them, right, and this reaction has been written in reverse, it looks like this, where we have the copper +2, the zinc metal, okay, and then on the other side of the arrow, we have the zinc ion and the copper metal. So notice how that happened, right? Okay, the zinc has switched sides, all right? The copper is still on the same side, okay, trying to point out how that works. Okay, and then in order to figure out the voltage of this battery that's made out of zinc and copper, what you will do then is look at the cell potentials, and here is your equation. The cell potential, right, or if you want to just think of it as voltage, is equal to the reduction potential minus the oxidation potential. So in this case, the reduction potential is positive 0.3419 volts, so that would be right here, minus negative 0.7618 volts, and you would get a positive 1.1037 volts. Okay, so that battery's got about 1.1 volts to it. Additionally, if your cell potential is greater than 0, then the reaction is spontaneous, meaning you don't have to provide any extra energy to make it happen. Running out of room here, spontaneous. Okay, it just happens. You put these things together, it's going to make an electric current. Okay, if the cell potential is less than 0, that means that battery is non-spontaneous. It does not automatically happen, and you're going to have to provide some energy to make it happen.